Okay, welcome everybody, and this is a preview for your comps. Now, the comps have many different parts. I'm only previewing the parts that I'm related to, which is the stats and epidemiology. The other ones, I'm going to upload a document for you, or you'll have access to a document that shows what you're expected to learn from the other areas. Obviously, knowing the comps are coming up, you've already been studying for them, right? I'm assuming that. And so this isn't going to be much of a problem. So this is my example. I'm going to go over each of these one by one in separate pictures, and I'll upload everything separately as well. So let's start. I think this is number one. Nope. Let's go to number one. Here we go. All right. So let's see. It says here, Table 1 presents the results of an analysis conducted by Dr. Rodriguez and his colleagues to assess the validity of a new screening test, the R test for disease D. A total of 675 individuals were screened from the general population. Of the 675, it is known that 75 individuals have disease D and 600 do not. Using the R test, 165 individuals tested positive for disease D and 610 did not. So I broke this down in this really nice table here. You have the marginal values. Here, these are the margins, right? These are marginal values. So it's broken down for you. Okay, so this is actually very timely now, given the coronavirus, and we're worried about testing. So first thing we want to know is, what is the estimated prevalence? So prevalence is the amount of current cases right now, whether they're new or they're existing or not, or new cases. That's prevalence. So prevalence is the disease, number of disease positives divided by the total, and I'm asking it per 1,000 individuals. That's my rate base. So you have 75 individuals, right? See, 75 individuals have disease, right? And there are 675 total individuals here. This corner value is the total of everybody. So it's 75 divided by 675, and I said per 1,000, so you multiply it by 1,000. You get 111.11 per 1,000, so that's your prevalence. So that's your disease prevalence. Second one, let's test the sensitivity. I'm going to try to keep this table up here. So sensitivity is the probability of testing positive given we're disease positive. So this is what's called a conditional probability. What's behind this slash is the condition, so you have to be disease positive. So only this column has the disease. This one does not. So we exclude everything else. We focus on this column. So now the question is, what's the probability of testing positive given one is disease positive? Well, of those 75, 65 test positive. So the correct answer is 65. So it's those testing positive divided by those who have the disease. So 65 of 75, 65 divided by 75 equals 0.87. So we'd say the sensitivity of the test is 0.87. Now let's go to this. Let's go to specificity here. Specificity is the probability of testing negative given one is disease negative, and we get 0.83. So let's go back up to the chart here. So we have the condition is that you have to have tested negative. So 600 tested negative, and so specificity is the probability of testing negative given you don't have the disease. So here 500 individuals tested negative of the 600, so that should be 500 divided by 600 is equal to 0.83. Okay, so let's go to the next one, which is right here. All right. How does population prevalence affect PPV? Okay, PPV is the positive predictive value of a test. The positive predictive value of a test. That means it's important that you listen to this. It means the probability that one has the disease given one tests positive. So see how that's opposite of what we did for sensitivity and specificity? So this is the probability of testing positive given one has the disease. PPV is highly affected by disease prevalence. So you see here I have two different tables. One for disease prevalence is 2%, and the other for disease prevalence is 6%. All right, so you'll notice also that I gave you this table and you have to fill everything out. If you know that the disease prevalence is 2%, and I give you a table like this, you notice there's 1, 2, 3, 4, 5, 6, 7, 8 of the 9 cells are empty. Only one cell is filled in, but I give you everything you need. I give you sensitivity and specificity. You can fill this cell in, these cells in pretty easily. Like, for instance, you know that the prevalence is 2%, so it's 0.02 times 10,000 gives you 200. Well, if you have 200 people who have the disease, 10,000 minus 200 equals 9,800. Those do not have the disease. Okay, and if we know the sensitivity is 0.98, well, we know that sensitivity is the probability of testing positive given your disease positive, so you go 0.98 times 200, we get 196. And same for specificity is a probability of testing negative given you don't have the disease. It's 0.93 times these folks here who don't have the disease, 9,800, you get 9,114. And then you can subtract one from the other because they have to sum up to 9,800. So 9,800 minus 9,114 equals 686. Now that we have these values, we just add them up and we fill up this table. All right, so we want to know what the probability of testing positive given, the probability of being disease positive given one test positive for the 2%ers. Well, we have here 882 people tested positive. You'll notice here that 196 of those people do have the disease and 686 do not. So there's a lot of false positives here, right? So it's 196 divided by 882, right? 196 divided by 882 equals 0.22. Now we do the same for the 6%ers. So it's the probability of being disease positive given you test positive. So here with the prevalence we have 1246 who test positive, and of those 588 are disease positive. So 588 divided by 1246 equals 0.47. So you see with the, well, first of all, in neither case is this PPV very high, but it's a lot higher when we have a higher disease prevalence. So that's something that you need to know, okay? All right, let's see what else we got. Now, I also ask you to calculate to make this calculation using our formula. If you remember from when we studied both stats and when we did epi, I showed you this PPV equation. Again, PPV is the probability of being disease positive given one test positive. So we can translate this. So I'm not going to go over everything how I get there now because we already did this in classes, but you need to know this equation because you're not always going to have access to a table. But you can calculate PPV using the following equation. So the numerator is going to be the probability of testing positive given your disease positive, which is the sensitivity, and probability of being disease positive, which is the prevalence. So if you get the sensitivity and the prevalence, you should be able to calculate this, right? And the denominator is the total probability of testing positive. So you can test positive correctly, or you can test positive incorrectly. So this is like the false positives, right? Probability of testing positive given your disease negative times the probability of being disease negative. So if you complete this equation, you can actually also get the exact same answer, and that's what we do. You should really write this down so that when you're taking the exam, if I ask you this question, you're ready for it. So remember, false positive is 1 minus specificity, and I'm not going to go into why that is right now because I already did in our courses. And if we do the calculation, fill in everything, just follow the step by step, you get the same answer for 2%, 0.22. All right. Let's go to the third one. This should be the third one, right? Make sure. Perfect. Okay, a professor wants to determine whether her department should keep a requirement for college algebra as a prerequisite for an introductory stats course. Accordingly, she allows some students to register for the course on a pass-fail basis, regardless of whether they have had the prerequisite. Of the 70 students in the class, 40 have had algebra and 30 have not. So not everybody had it. At the end of the semester, the professor compares the number of students passing or failing a class with whether they had algebra. The results are presented below. Below, it meant below. Are students more likely to pass the course if they had taken college algebra? Okay, all right, so we want to see what the odds are of passing if one has had algebra versus not having algebra. Now, I mean, you could also do this with a chi-square test, but that's not what the purpose here. I just want to see if you can do the odds ratio. So we start by writing the null and the alternative hypothesis. Well, an odds ratio of 1 means there is no difference between the two, because odds are probability of success, which is passing, divided by probability of failure. And we're comparing algebra to no algebra. So if the numerator and the denominator are equal, then we have nothing. So odds ratio is a ratio of odds. So the odds of passing if you have algebra divided by the odds of passing if you have no algebra. So if they're the same, you're going to have an odds ratio of 1. That means there's no effect. Our alternative would be that the odds ratio is not 1. It could be greater, whatever you want to do, but I'm just going to do it. This is called a two-tailed test, right, with alpha at 0.05. And we'll need that because I'm asking you to calculate something. We're not doing a statistical test per se here, but I'm asking you to do certain calculations. We need this alpha. So calculate the appropriate odds ratio. So the odds ratio is the probability of success divided by the probability of failure. So 34 passed and 6 did not, right? Who took algebra? So that's 34 divided by 6. And among those who did not take algebra, 12 passed and 18 failed. 12 divided by 18. And, you take the if I bring the denominator into the numerator, I have to flip them around. I get 8.5. So this is telling me the odds of passing the course are 8.5 higher if you took algebra than if you didn't take algebra. So you're a lot more likely, 8.5 times, almost 9 times more likely to pass. Cool. And the confidence interval. Now, the confidence interval, you have to remember this equation for the odds ratio. So the confidence interval is basically 1 divided, the reciprocal of each cell, 1 divided by A plus 1 divided by B. And what I mean by A, B, C, D, it's just like this is cell A, this is cell B, this is cell C, this is cell D. So it's this square root of 1 divided by 34 plus 1 divided by 6 plus 1 divided by 12 plus 1 divided by 18, which you see I did right here. I get 0.57876, and we need the standard error in order to complete this equation for the confidence interval. So if you look at the 95% confidence interval, I have E, or Euler's number, raised to the natural log of the odds ratio plus or minus whatever the margin of error. So we have to calculate this margin of error. So the margin of error is our z value for whatever our alpha is. So remember, z value is related to the standard normal distribution, alpha divided by 2, because it's two-tailed. You always have two tails, obviously, when you're doing a confidence interval, because you have below and above, times the standard error of the odds ratio. I'm not going to even talk about what that is right now, because you should know that from our courses. And we raise this because, well, we have to deal with the fact that we're taking a natural log of this value, because the odds ratio itself is not normal. It's not normally distributed. So we're taking a natural log of that value. Sad, it's not normal, huh? So it's abnormal. So our z value for alpha of 0.05 divided by 2 is standard 1.96. So margin of error is 1.96 times that standard error right here, and we get 1.13438. So to get now the reason we have to raise it here is because we have to bring it out of this natural log form and bring it back into a non-log form. So we take the natural log of the odds ratio, which is ln, stands for natural log. So now the odds ratio is not in a natural log form, but we're going to convert it into natural log form, which will give us the log odds. We call this the log odds. So this 8.5 translates to 2.17475. So now we have E, Euler's number, raised to 2.17475 plus or minus this margin of error. It's plus or minus because, again, it's above and below the whatever our value is. At the lower end, we get e raised to 1.0437. At the upper level, we get e raised to 3.30913, and this is what we get. This is our again, it's e raised to this value, so we have to use your calculator. You have to convert this back to its non exponential form. So we got 2.830 and 27.361. So what this means is the odds of passing the class if you had the prep course are 8.5 times higher than if you didn't take the prep course, and that value can be anywhere between 2.830 or 27.361. Now I say reject the null because if this confidence interval includes 1, then that's not good, because again 1 means that there's no relation between the two. But here it does not include 1, so we can reject the null. Again, I'm not going to go into why that is because I spent a lot of time talking about that in our courses. All right, let's move on. MoveOn.org. That's from a movie. A couple other things. Let's see. Here's some more questions that are more general. If you are conducting a case control study, is it appropriate to calculate relative risk? If so, why? If not, what is the appropriate measure associated between exposure and disease? So relative risk means new cases, right? So like incidence. So when we're doing a case control study, we're comparing people who have the disease to people who don't have the disease to look at that exposure. So we're kind of going backwards in time. We're going back to the future. We're going backwards in time. So relative risk doesn't make sense. So instead of using relative risk, you use the odds ratio, because the odds ratio doesn't matter if you're going forward or backwards. So that's what that is. Research from the Rodriguez Institute conducted a prospective study to identify the incidence of HIV in a local community. They followed 25 individuals, 5 years. Of the 25 individuals at baseline, there were 6 new cases of HIV infection during the 5-year period. What is the incidence rate per 1,000 people of HIV infection, accounting for person time? So person time, this is whenever we're doing longitudinal studies and we have repeated measures, we have to account for people, how much time each person spends in the study, right? So if we're doing, so actually I have this chart, here it is. So if we have 5 years, right? We have 25 individuals and we have 5 years. Now ignore for a second that there are dots here. Imagine these are all filled with X's. So let's ignore that, okay? So I'm ignoring the dots. So if each of these individuals was here for the first year, as everybody was, and imagine they were all here for the second, third, fourth, and fifth year, each person would contribute 1 person year. So in this first year, we have what are called 25 person years contributed. If everybody was here, they would have contributed 25 in the second, and again here 25 in the third, 25 in the fourth, and 25 in the fifth. So 5 times 25 would be 125. Now in some case, well, as is the normal case, people end up being lost to follow-up, or they just are missing for some reason or another. Like this person here, now person 12 was here for the first year, but then dropped out of the study for whatever reason. Or it could have passed away too. So the second year, then we have 1, 2, 3, 4 dots, right? That means 4 dots are the universal term for missing. So 25 minus 4 is 21. So the first year we have 25, second we have 21, third we have 19, fourth 19, and fifth year 17. So this is more realistic, but I'm going to ask you both of those here, right? So you need to be able to answer both. So let me get back over there. So the first question is, what's the incidence rate per 1,000 population of HIV infection accounting for person time if there was no missing data at all, right? If there, no, this should be there were no missing data. This is my pet peeve. Missing is, data is plural, the word data. Dang, I messed up myself, so please apologize for that. So this is 6 divided by 125 times 1,000. It was 48 per 1,000. Now, if what we see in table 4, we already calculated that with table 4 accounting for missing data, there's 101 individuals in the person years, excuse me. And the sample, so we go 6 divided by 1001 times 1,000, get 59. So if we just assume everybody is there, we actually are underestimating our, what is this we're talking about? Our incidence rate. So that's not good. Okay, so we want to make sure we don't do that. All right, let's go to the next one, 11. If the correlation coefficient between A, so here we're talking about correlation coefficients. So again, we already covered what that means. That's just measuring how two variables are related. So if the correlation coefficient between variable A and B is minus 0.46, how much of the variation between the two variables is shared variation? Well, R is a standardized measure of association between two variables. R squared talks about calculates the variance shared among the two variables. So R squared is a proportion of shared variance, so you just square it. You got 21 with 0.2116 and ask for percentage, so multiply this by 102, goes 21.6 or just 21%. So that's a shared variance. That's saying that 21% of what we see, the variability we see in the two variables is shared variance. Here's a multiple regression equation. Explain what each term is. So this is a multiple regression equation. It's a prediction equation, right? We're just actually looking at the predictive value. That's why we don't see any error term here, right? So this is the predicted value. So these b's here are coefficients. The first one, the b sub 0, there's no x by it, right? So this is the intercept value. So this is like a line, right? And here we have two predictors. So actually, I guess that would be a plane. Am I right? Because we have two different predictors. It's x1 and x2. So and our outcome is whatever y is. So here we have b0, b1, x1 plus b2, x2. But just let's imagine it as a line. It makes it just a lot simpler to think about it. So y hat stands for the outcome, and the little hat means it's estimated. Beta 0 is the intercept, beta 1 is the slope for variable 1, x1, and beta 2 is the slope for variable 2, x2, and the x1 and x2 are two different variables. I could have given them whatever symbol you wanted. It could have been z, q, whatever, okay? Okay, suppose you conducted a multiple regression analysis to assess the effects of smoking status. 0, 1 means does not smoke, 1 means smokes, and income in dollars on weight in pounds. So this y represents weight, because the outcome is always going to be the y, or whatever the variable is out here, right? The following is a regression equation along with the p-values. Ooh, I like that. For smoking, p equals 0.07. For income, so p is the probability of the observed result given the null hypothesis is true. In regression equations, the null hypothesis is that these b values are equal to 0. So this would be the probability of observing this value if, in fact, the b value is 0. Okay, so for 7.07 for income, for smoking, 0.04 for income. Which of the two variables has a significant effect on weight if alpha is 0.05? So alpha is the probability of a false positive result, rejecting the null hypothesis when we shouldn't have rejected it. So interpret the results. Okay, so if our alpha is 0.05, we're looking for a p-value that's less than or equal to 0.05. And the only one that fits here is income. Okay, so income seems to be the best predictor of weight. Now, some people would argue that 0.1 could be used, but I told you I wanted 0.05 here. So whatever you decide in advance, that's how it goes. So the only significant effect you have is of income. All right. So how do we interpret this? So this is saying for each 1 unit increase in income, so units are dollars. So for each dollar increase in income, there is I had the wrong value here. Yeah, see, that's wrong. I'm sorry, that's my mistake. It should be 0.36, not 0.96. It should be 0.36 decrease in pounds holding smoking status constant. Now let me explain why I did that. So this is negative, so that means it's a decrease. So when we interpret this, we have to talk about a unit increase. So we know what our units are here. For income, it's $1, right? Each unit for income is $1. For smoking, you're just going from 0 to 1. So if we were to interpret smoking, I'd say going from 0 to 1, going from not smoking to smoking, there's a 0.96 decrease in weight, right, in pounds. But this isn't significant, using alpha of 0.05, okay? Now, notice I always say holding the other variable constant, so that's important because when you're interpreting this, it's as if this value is held constant. It means everybody's given the same value, the mean value for whatever this variable is. Okay, so that's how you'd interpret this. But remember, it should be, in this case, it should be 0.36. Okay, so let's move on. I think we have one left. Yeah, this is it. Suppose you want to test a new drug that is designed to cure a common cold. Imagine that you want to compare the new drug to zinc tablets, vitamin C, and a placebo. What type of study is the best to test the new drug? Well, it would be an experimental study, a randomized controlled trial. You'd randomly assign individuals to any of those 4 conditions. The placebo means it's a sugar pill or it's some inert substance. So the placebo is going to have what's known as a placebo effect. Well, people will expect it to work just because they're taking it. So you're hoping that your drug works better than expectation. That's how we do tests, by the way, when it comes to drug. What would be the null and the alternative hypothesis? The null hypothesis is that there's no difference in mean cold symptoms among the different treatments. The alternative is that there is at least one, man, I cannot write straight, can I? There's at least one difference in mean cold symptoms among the different treatments. What would be the ideal statistical analysis? Here would be ANOVA, analysis of variance, because we have more than 2 groups. We're comparing means. What would you select for your probability of a type 1 error? That's, like I say here, it's subjective. Most people have this tendency to want to use a heuristic and they select 0.05. It depends. If you have a very small sample size, you can go higher. If there's some risk of making an error, like somebody could die, you usually go lower. So it depends. There's a lot of that's a power issue. Oh, here's another one. Suppose you wanted to conduct post hoc testing. Post hoc means after the fact, right? How many possible pairwise comparisons could we do? Dang, that's a good one, right? This is binomial coefficient. So this tells us how many ways we can arrange whatever the n value is r at a time. So these are post hoc pairwise comparisons. So the problem with ANOVA is it's an omnibus test. It just tells you if there's an overall difference. But people are interested in, like, wait, was zinc better than the placebo? Was this vitamin C better than placebo, etc.? So they want to know those. So you can make a whole bunch of comparisons, but if you make too many, what happens is you'll see here, you increase the probability of a false positive result. So we use this equation here, or binomial coefficient, which is n factorial divided by r factorial times n minus r factorial. This factorial sum is just like n times n minus 1 times n minus 2, etc. But you can't have a 0 there, because 0 then would make everything equal 0. So 0 factorial is equal to 1. So eventually you'll get to that. So how many possible comparisons do we have? So we have, in this case, we have 4 groups, and we're comparing them 2 at a time. So it's n is equal to 4. So it's 4 factorial divided by 2 factorial times 4 minus 2 factorial. We end up getting 6, right? And this is kind of easy because 4 factorial is 4 times 3 times 2 times 1. So 4 times 3 times 2 times 1. 2 times 1 is the same as 2 factorial, so those can cancel out. So you get 4 times 3 is 12, divided by, again, 4 minus 2 is 2 factorial. So it's 2 times 1 is 2. So we get 6. 12 divided by 2 is 6. Okay. What is the family-wise error rate if we don't adjust? Now, people like to just do every possible t-test. T-test is what they tend to do when they just make these comparisons, but the problem is that'll inflate the type 1 error. So let's look at this. The probability of at least one false positive result is going to be 1 minus the probability of having no false positive results. So probability of false positive result is 0.05. No false positive results is 0.95, right, for 1, because this is actually power, right? So we have 1 minus 0.95, so this is like not having any false positive results. So it'd be 0.95 to the 6. So the opposite of having none is at least 1. That's why we're doing 1. So in probability theory, all probability of all possible mutual exclusive events in a sample space must sum to 1. So here we have 0.95 to the 6. So 1 minus that is 0.265, or 27%. Right? So again, I multiply this by 100. That's 26.5, or 27%. So what happens is if we can calculate every possible pairwise comparison, we have a 27% chance of a false positive result. So our alpha increased from 0.05 to 27, or from 5% to 27%. It really sucks. What is the easiest way to reduce the possibility of inflated type 1 error? You do something called the easiest way. It's made as a Bonferroni correction. So you divide alpha by the number of tests you conduct. So if alpha is 0.05, and if we decide to conduct 6 tests, you'll be 0.05 times divided by 6. And the reason this is because that'll maintain that the overall alpha for all tests would be 0.05. For each test, it would be a sixth of that. And that's it. So if you can do this, you are ready for the test. Enjoy, study hard. Thank you. Bye.